Okie doke. Hello everyone. So I'm going to show us some stuff about the electromotive force internal resistance of a cell. Whoops. Called practical for those of us who want to recap or haven't done this. Okay. So it was all about trying to find the electromotive force, which was the sum, the sum of the potentials that could be provided by a power supply. So the sum of the energy per unit charge that could be from a power supply, right? So you could be thinking of a cell, a battery, any type of thing that provides power. Okay, so a potato battery, it is a type of battery. It's an electrochemical cell, right? And if we take the chemicals of zinc and we take the chemicals of copper, they react with each other, which produces a chemical energy. And then this chemical energy is converted to an electric energy by the spontaneous electron transfer that starts to happen within our potato. Okay. You could actually possibly do this on your own. You could find some of the lower denominations of the coin have copper in them. So you could use a coin. You could use a zinc nail or something like that. Zinc paperclip. Have a look at what it's made of. If it's magnetic, it's going to be iron, steel, nickel, or cobalt. Okay, so let's talk a little bit more about this work. The potato basically acts as a buffer and as an electrolyte for those two metals that we had. The copper and the zinc. And that means it's basically separating them because it's acting as a buffer. Okay, and it forces the electrons trying to get from one metal to the other to travel through the potato and form a circuit, right? The electrons are able to, flow through the potato because it acts as an electrolyte. The two metals would still react if they touched each other, without the potato being that buffer, without the potato being that medium in between. But without the barrier, without the electrolyte, the energy released from the reaction wouldn't form a circuit because it's not allowing that spontaneous electron transfer. So that's why you wouldn't get power in your circuit, whether you're using that to, go to a light bulb or something like that, right? So basically, I'm going to take this zinc and I'm going to, put this in here. I'm going to take this copper, I'm going to put this in here. The only risk really in this experiment when using the potato cell is I could have cut myself on, these bits of metal. Besides that, we're pretty safe. After that, we're going to set it up like in the diagrams that we've seen. Crocodile clip to copper, crocodile clip to zinc. I'm going to want an ammeter here. I've got the ammeter with the milliamp attachment because we're not really going to be getting a noticeable current out of this. If we were, we would be using this sort of thing. We'd be using spots to power loads of stuff. We're not because it kind of sucks. Okay, so we're going to pop that into the ammeter. We're going to get ourselves a couple more wires. We're going to attach this into a variable resistor. Now, I've got the rheostat out as a variable resistor because that's the nice sort of tactile visual thing of me changing it. But I could just be varying my resistor by just putting in different resistors. Finding different band resistors of different resistances and swapping those in and out. But just for the sake of this being visual, I want to put the rheostat there because it's fun to slide along. I'm going to put the rheostat in there. I'm going to connect it to the top here so I get that sliding function, and I put too many wires in. Okay, don't need that. Okie doke. So, am I getting a current? Yeah, I'm getting a current here of 0.43 milliamps. So I am getting something from the potato cell. I'm going to attach a multimeter here, and I'm going to set that to the voltmeter mode. Because then I can get some of those milli readings. That wire's no good. I need a long one. Here we go. I'm going to attach it to the multimeter because then again I can reach the millivolt settings, and I'm getting a really small noticeable PD through there. And if I change that, these values start to change slightly. The reason that we're putting this variable resistor in, or we're swapping out for different resistors, is because I want different terminal PDs coming out of my potato cell. Now, unlike our power supply, yeah, here's a basic one over here. Unlike our power supply, which I can change the terminal PD really easily by turning along this knob, by turning this dial, which is essentially acting as an internal resistor, a variable resistor, changing what's coming out. My potato does not have that. Yeah, I have not seen potatoes which have dials on turning up and down. If you have, let me know. We don't have that. So the variable resistor, just think of it basically as acting as that dial on the front, so we can kind of control the terminal PD coming out. Otherwise, we just have that one terminal PD of the potato cell. I'm going to try and plug this into the light bulb. I'm not confident, just to see if this lights up. Okay, see if that. No, wonderful. I didn't think so based on the readings I was getting on my equipment there. But there's always hope that there'll be light in this world. So you could give this a go if you find a penny and if you have the appropriate wires and stuff. I don't know if you do. But that's basically how we set up the circuit. That's some of the chemistry that's going on inside. You'll notice a lot of that chemistry isn't in the spec, so I wouldn't worry about that too much, but just to give you a little bit of background. And I think next time I'm not going to get free pat potatoes because the ionic composition of these potatoes doesn't seem so great. We're not getting noticeable results of them. Okie doke, good stuff.